Okay, so here we got the notes for section 3.1, exponential and logistic, functions. So down here, exponential functions in the graphs. So the functions x squared and 2 to the x each involve a base, the x and the 2 raised to a power, but the roles are reversed. So for x squared, the base is the variable x, the exponent is the constant 2. For g of x, the base is 2, the exponent is the variable x. So down here we have the definition for exponential functions. So let a and b be real number constants. An exponential function in x is a function that can be written in the form f of x is equal to a times b raised to the x to the power. Where a is non-zero, b is positive, and b is also not equal to 1. That happens if b is 1, this equation just becomes a. b is 1 to any power is 1, and a times 1 is 1. The constant a is the initial value of the function, and b is the base. So here, determine whether the following functions are exponential. So for this first one, it is yes, because it's a number raised to a power. This one is no, because it's x to a number, not number to x. This one is yes. This one is yes. And this one is, the last one is no, because there's no x involved. Pi is not a variable. All right, well, spacing it off. So example 2, for f of x equals 2 to the x, find the following. F of 4, so my function is 2 to the x. We'll jot that down here. F of x is equal to 2 to the x. So f of 4 is going to be 2 to the 4th, which is 2 times 2 times 2 times 2, which is 16. F of 0 is 2 to the 0th, which is 1, because anything to the 0th is 1. F of negative 3 is 2 to the negative 3, which is 1 over 2 cubed, which is 1/8. If f is 1/2, this becomes 2 to the 1/2, which is just the square root of 2. And if f is the negative 3/2, so this would be 2 to the negative 3/2. So a couple things are going to happen. The negative actually puts it on the bottom of a fraction. The number here on the bottom of the exponent is actually a type of root. So this is the square root of 2 cubed, and then I can work out what 2 cubed is. So this is 1 over the square root of 8. Normally you don't leave radicals on the bottom, so this is root 8 over 8. Root 8 simplifies as root 2 over 2, so oops. 2 root 2, and there's still an 8 on the bottom here. So this is all root 2 over 4. Would be the final simplified version. All right, so let's see here. So determine the formulas for the exponential functions g and h whose values are given in the table below. So we're actually going to start here at x equals 0 because this row gives me my value for a. So this is going to be 4 times something to the x, and this one's going to be 8 times something to the x. And this value is actually the multiplier, what you are multiplying by as you go up. So in this case, to go from 4 to 3, I just said it, to go from 4 to 12, to go from 12 to 36, I'm multiplying by 3. Over here, to go from 8 to 2 and 2 to a half, this one's tricky because I'm dividing by 4. I'm dividing by 4 every time, so the multiplier is 1/4. So if you need to divide, your b value is going to be a fraction. So I'm dividing by 4 each time. Okay, so we got the definitions for growth and decay. So for any exponential function a times b to the x and any real number x, f of x plus 1 is equal to b times f of x. So essentially as x counts up, you are multiplying by some value b. So the next term in your table is the multiple of the previous number. So that's how I did this up here. The next term is, so the multiplier is 3, so that tells me my b value must be 3. If a is positive and b is more than 1, the function f is increasing and is referred to as a growth function. B is the growth factor. If a is greater than 0 and b is less than 1, so that would be this case over here, we have a decay function. The base b is the decay factor. So essentially this is growing because the values triple each time x counts up. This is the decay because the values are going down. They're being divided by 4 each time x goes up. Okay, so example 4, describe how to transform the graph of 2 to the x into the graph of the given function. So Let's see if we can come up with, so we get a times b, so it's going to be x minus h, and then plus k at the end, where x, where h and k do the same thing that they've always done, where they shift the graph left to right, shift the graph up or down. So if this is 2 to the x minus 1, remember it does the opposite, so this graph is just moved right 1 unit. Putting a negative in front of the x is going to serve to mirror the graph, because that's what changing the sign does. It mirrors the graph left to right. So this is a y-axis reflection. If you put the negative all the way out front, that's going to mirror the graph on the x-axis top to bottom. So this one is just a vertical stretch of 3. The graph's going to be 3 times taller than it was before. Okay, down here, so we got the definition of the natural base. So the limit means as you let x get very, very large, this thing, 1 plus 1 over x raised to the xth, will approximate this value e, which if you want the decimal value for it, e is approximately 2.718281828. Now it looks like there's a repeating pattern, but there's not. E is an irrational number like pi, it never ends. All right. Exponential functions on the base e, so any exponential function a times b to the x can be written a times e to the kx, where you choose some value k essentially to make e to the k the same thing as b. So if a is 0 and k is greater than 0, you have a growth function, and k is less than 0, you have a decay function. So let's see here. So describe how to transform the graph of e to the x into the graph of the given function. I bet this one's going to roll over to the next page too. So the rules still work the same, just like if it was b to the x. So this is going to be, since I'm messing with the x value, this is going to be a horizontal compression by 2, or a vertical stretch by 1/2. So I'm going to look at the graph just real quick. So e to the x, or versus e to the 2x. Whoops, went to the wrong menu. There we go. You need to listen to me type things into my calculator. E to the x, e to the 2x. There we go. So this is a horizontal compression of 2. Because remember, horizontal things always work backwards. If I put a 2 all the way up front, that's y. If you put something up to the x, that's horizontal. And it's always the opposite of what you would expect. So that's why this one was right 1. So this one you think you would multiply by 2 and make it wider, but you actually compress it and shrink it down. Let's see what the next page is. Yep, rolls over. Okay. So e to the negative x. So this is a y-axis reflection. And this is a vertical stretch by 3, so multiplying it by 3. Okay, here we have the formula for a logistic growth function. So a, b, c, and k be positive constants with b less than 1, so between 0 and 1 for b. A logistic growth function in x is a function to be written in the form this, or this if you want to use e, where c is the limit to growth. So a logistic growth function essentially is a population equation. So the graph starts slow, rises, and then eventually levels off, and it levels off at this value of c. So populations will grow until there's not enough material, supplies, room, whatever you have, and then population will flatten off. So if you make b greater than 1 or k less than 0, you get a logistic decay function, which just mirrors the function. So the population falls like that. So by setting a equal to c equal to k equal to 1, we have the basic, most general logistic function possible. So here it says find the y-intercept and the horizontal asymptotes of the following functions. So the y-intercepts, or the y-intercepts, sorry, occur when x is 0. So I need to find f of 0. So that's going to be 8 over 1 plus 3 times 0.7 to the 0th. So anything to the 0th is 1, so this becomes 1 plus 3 on the bottom, because 0.7 to the 0th is 1. 1 times 3 is 3. So this is 8 over 4, which is just 2. The horizontal asymptotes, we can look at the graph. One of them is going to be this numerator. So we're going to have 1 at y equals 8, and we probably also have 1 at y equals 0, but let's look at the graph just to be sure, because normally you always have 1 at y equals 0. So 8 over quantity 1 plus 3 times 0.7 raised to the x. Syntax error. Too many parentheses? Probably too many parentheses. Let's delete that one. Yeah, there we go. Yep, the other one's y equals 0. Similar thing's probably going to happen down here. So to find the y-intercept, we're finding f of 0. So that's 20 over 1 plus 2e to the negative 3 times 0. So this becomes e to the 0th. So e to the 0th is 1. 2 times 1 is 2. So this is just this. So 20/3, which doesn't reduce. To find the horizontal asymptotes, you're going to have one at y equals 0, because you always do. And the other one is whatever the numerator of the fraction is, 20 in this case. Okay, so population models. So example 7 here says, using the data in the table and assuming a growth is exponential, when did the population of Austin, Texas surpass 1 million persons? So I'm going to set this equal to 0, which means that this value here is at x equals 5. So I have my equation. Growth is exponential, so I can do this generic equation. Now, I do know x and y values, so I can actually use that to solve this equation. Now, if I set x equals 0, that makes this my a value, because if I do this, 815,974 equals a times b, which I don't know, but my x value is 0 for this row. So this just becomes, that goes away, so there's my a value. So to find b, I can use this row. So 931,830 is equal to 815,974. That's my value for a that I just calculated, times b. And at this point, my x value is 5. So I need to divide that across. So 931,830 divided by 815,974 gives me 1.141984916 equals b to the 5th. And to get rid of a 5th, you can think about 2 ways. You can raise everything to a 1/5 power, or that's the same thing as taking the 5th root. But your calculator will probably like the 1/5 power better. So b is 1.027, we'll round it there. So that means my equation is y equals 815,974 times b, 1027, raised to the x. And I want to know, when does it surpass 1 million people? So put 1 million in for x. I think that's a million. Yep. 815,974 times 1.02 raised to the x. And from here, it's guess and check, essentially. So, or if you actually graph this function, actually we'll do it that way. We're going to graph this y equals equation. So 815,974 times 1.027 raised to the xth power. Draw. And then I want to, let's see, G-solve. I want an x calculation. So I'm solving for, so I want to know, when is the y value 1 million? Uh-oh. I didn't have my zoom set. So zoom, we'll do auto here. See if that'll fix it. Gsolve X calculation, because I want a Y value. Still not finding it. Zoom out. Zoom out. So I'm just zooming my graph out. If you have Desmos, you can do a similar thing. So if I zoom, there we go, finally zoomed out far enough. So on the graph, X is 7.63. But my table, I counted my X values from 2010. So this would convert to about 2017 and 6/10 of the year. So, January, February, March, April, May, June is so probably sometime around July 2017, because it's a little bit more than halfway through the year. Okay, example 8, based on longitudinal census data, a logistic model for the population of San Diego, California, T years after 1900 is as follows equation. According to this model, when did San Diego achieve the 1 million mark in population? So similar setup. We can look at the graph of that, get our zoom correct, and then figure out where 1542444 over 1 plus 54082 e to the negative 0.05397. Your calculator doesn't care, so just x. Let it draw. So zoom auto. Gsolve X calculation. So when is the Y value? 1,000,000. 3, 1, 2, 3. I didn't find it again. Zoom out. Let's see if we find it now. Gsolve. Hey, there we go. So I get a goofy number here. I get an X value of 213.3, which doesn't make sense, because if I add that onto 1900, that gives me the year 2113, so let's go back to make sure I type my equation right. 1542 quadruple fours. Okay, that's right. 1 plus 54082 e to the negative. Well, this just doesn't make any sense. I could work the math out, but now I'm invested in figuring out this out on my calculator. Because obviously, it's not going to be 2113. Unless I accidentally put a billion in. Trace. Nope. Well, that's my answer. It's probably wrong. I'll figure out what it is. If you figure out what it is, let me know. But I'm not going to let you listen to me figure it out. All right, that's the end of the section.